Okay, it's third week of the first term. That's SABIS Chemistry Grade 12. And material is good also for people taking the AP Chemistry exam. So let's start.
In the lab where sparks ignite, beakers bubble in neon light. Equations dance, my heart takes flight. K-chemistry.com, oh yeah, mixing science love. No despair with Mr. Hesham, it's crystal clear. My new love's in the atmosphere. Periodic tables, they sing to me. Carbon bonds like destiny. Every element sets me free. From molecules to the stars above, this is more than science, it's love. K-chemistry.com, oh yeah, mixing science love. No despair with Mr. Hesham Mahmoud. It's crystal clear, my new love's in the atmosphere. He's the catalyst, I'm the reaction. Energy flows, pure attraction. Balancing equations, life's new faction. K-chemistry.com, oh yeah, mixing science love. No despair with Mr. Hesham Mahmoud. It's crystal clear, my new love's in the atmosphere. Periodicist, I'm the reaction. Energy flows, pure attraction. Balancing equations, life's new faction.
Let's read the first question together. Real gases are expected to deviate the least from the expected ideal behavior at blank pressure and blank temperature. The choices are low, high, any, or intermediate. Now think about it. Real gases behave most ideally when they don't interact much. When did this happen? This is going to happen at low pressure. When there is less pressure, we are not forcing the particles together, so there is no interaction between them. Remember, less interaction, it will be more ideal. What about the temperature? At high temperature, the particles are moving very fast. That weak attraction forces don't have time to matter. So the correct answer is real gases expected to deviate the least from the expected ideal behavior at low pressure and high temperature. So I want to make sure you got this right. So tell me, what happens if gases are at high pressure and low temperature? The answer is that they deviate the most from ideal behavior. They become more as real gases. The particles are crowded here, close together and moving slowly, so the attractions and repulsions really start to matter. And here is the next question. So I have equal masses of neon and hydrogen gases mixed in the same container at 26.5. We're asked to compare their kinetic energies and their molecular speeds. First, remember that at the same temperature, the average molecular kinetic energy of all gases is the same, no matter what the gas is. So neon and hydrogen have the same average kinetic energy, but speed is different. The lighter particles move faster. According to Graham's law, velocity is inversely proportional to the square root of the molar mass. So the velocity of the first one, which is hydrogen gas, versus the velocity of the neon gas is equal to the reverse. So the inversely proportional means that the molar mass of the neon will be here, while the molar mass of hydrogen will be here. You know that the molar mass of neon is 4, and the molar mass of hydrogen is 2. So if I get the square root of 4 over 2, sorry, that's not helium, that's neon. So it's not 4, it's 20. So I would say 20 over 2. This means that you need to get the radical of 10. That is equal to 3.16. This means that the hydrogen molecules move about 3.16 times faster since they are smaller than the neon molecules. So the answer is the average kinetic energy of neon is the same as that of hydrogen gas, and the average molecular speed of neon is 3.16 times less than that of hydrogen gas. Remember, neon is heavier, that's why its speed is less than that of hydrogen, which is lighter gas. Now let's see the checkpoint of the kinetic molecular theory of ideal gases. Which postulates are correct? First, particles do collide with each other and with the walls of the container. That's true. And those collisions are elastic. Second, the average molecular kinetic energy of particles is proportional to the Kelvin temperature of the gas. That's also true. Temperature is directly tied to kinetic energy. Third, the individual volume of each particle is negligible compared to the container volume. That's another postulate. But watch out, saying the molar volume is 22.4 liters is not a postulate. It's just the conditions at STP will make it equal to 22.4. But if the conditions is different, then the molar volume is different, and that's not a postulate anyway. Saying that particles exert attractive or repulsive forces is also false. Ideal gases are assumed to have no intermolecular forces. So, like in the last question, we said the more you are ideal, the interaction will be minimal. So, the correct postulates are elastic collisions, negligible particle volume, and kinetic energy proportional to temperature. Let's now have a look at all of them, all the postulates. These are all the ones that we need to understand and memorize very well. Make sure you know all of these postulates, understand them very well, because this is a very common question in the AP chemistry exam. I really envy those particles moving all the time. I bet they never get fat. Okay, this is our next question. Find the number of moles of gas collected over water. Sometimes in some experiments, the gas is produced and need to collect it over water. The volume of the helium gas collected was 72 milliliters. When the water levels inside and outside the tube were the same, and this is very important point. So the level water inside here and outside the container were the same. That means that the pressure inside the tube equals to the atmospheric pressure coming outside. First, let's note the data. The atmospheric pressure is 765 millimeter Hg, temperature 303 Kelvin, and the vapor pressure is 303 Kelvin. At 303 Kelvin is 26 millimeter Hg. Remember, when we collected the gas, the total pressure includes both. What are the two gases inside here? There is the gas that I'm talking about, the helium gas, plus the water vapor. So there is some water vapor coming from this one. When it is evaporated, it comes up. So the pressure of the helium plus the pressure of the water vapor equal to the outside pressure, which is the atmospheric pressure. This means that the 765 is equal to the pressure of the helium, and the pressure of the water, we mentioned that it is 26 millimeter Hg. So if you want to calculate the pressure of the helium, all you have to do is subtract both sides by 26. So the pressure of helium is equal to 765 minus 26 gives us 739 millimeter Hg. Now we need to convert that information into atmospheres. But why do we need to convert it into atmospheres? Because the required to find in the question actually is finally the number of moles of helium. And you need to find this using the PV is equal to nRT. Remember, whenever we are using this equation, the unit of the pressure has to be in atmospheric pressure. Nevertheless, he is asked us to find the pressure in atmospheric pressure. So we say that the 739 millimeter Hg that you have, what's the conversion factor? 760 millimeter Hg is equal to 1 atmospheric pressure. So we need to divide 739 by 760. That's equal to 0.972 atmospheric pressure. Now to the last step. We'll apply the law PV is equal to nRT. So, and dividing both sides by RT. So, we need to get the number of moles. So divide this one by RT, divide this one by RT. So N is equal to PV divided by RT. The pressure we just calculated as 0.972. The volume is mentioned here, should be in liters all the time. Is it in the liter? Yes, it is 72 milliliters. So I have to change this one into liter. That's 0.0720. How did you do that? By dividing 72 by 1000. And then R is a fixed value always given, that's 0.0800, and the temperature has to be Kelvin in the all the time. It is 303, luckily it's already Kelvin, so we'll do our math calculations to find the result as 0.00289 moles of helium. And remember that we need three significant figures. There is three significant figures here, and so I have already three significant figures, so this is my correct answer. Okay, in this question number 5, I need to find the volume of one of the titrants against other one. So I'm making titration between dichromate, between potassium dichromate, and between vanadium. There are two methods to answer this. The indirect method, which some people find it a little bit easier and direct, and it's rare to make a mistake in this one. And we can see the ratio says that I have 6 moles of this one reacting with 1 mole of this one. What did he give me? Give me the milliliters, the volume, and the concentration of the dichromate. So I can say that C is equal to N over V. So N is equal to C multiplied by V. What is the C? That's 200, 0.200, and the volume is 25, but I have to change it. So 25 over 1000. Why? Because this is molar, so I cannot use milliliter. I have to use liter. So I will find the number of moles that's equal to, for the dichromate, that's equal to 0.00500 moles, and I know that the ratio is 1 to 6. So if I need to change the number of moles, if I need to change the number of moles of this one, I can make bi-dimensional analysis. So number of moles of dichromate of K2Cr2O7. Sorry, this is for vanadium. This is for vanadium, K2 plus. I can multiply it by the conversion factor, which tells me that 6 moles of vanadium 2 plus. I put it at the bottom so it is vanadium cancels with vanadium. And I put the dichromate at the top, 1 mole. So 1 mole reacts with 6 moles, and then I cancel this one with this one. So basically, if you want to find the number of moles of dichromate, divide this one by 6. You will get 8.33 times 10 to the power of -4 moles. And then this, you need the volume of the dichromate, not its moles only. So again, with the same equation, if N is equal to CV, so the volume is equal to N over C. So that's 8.33 times 10 to the power of -4 divided by the volume divided by the concentration of it, which is equal to 0.100. And then I have to multiply this by 1000, so I can get it as, I can multiply it by 1000. So let's do it. 8.33 times 10 to the power -4 divided by 0.100 and multiplied by 1000. I will get 8.33 milliliters. This is the indirect method, and it's a little bit easy to do and not to make a mistake, but a little bit slow. You can do the direct method. The direct method actually is a faster method and depends that we know the ratio in the titration directly. Remember, if in another situation I have, for example, titrating HCl and NaOH, and the ratio between them according to the balance is 1 mole reacts with 1 mole. So N is equal to C multiplied by V. If the ratio is the same, so number of moles is 1 to 1, so the C multiplied V of the HCl equal to C multiplied by V for NaOH. So I can say just CV equal to CV. One of them is not available, I can get it. So for example, if I don't know, like in this question, I don't know the volume of the second one, I can say C1V1 over C2 directly. But here the ratio is not 1 to 1, the ratio is different. What is the ratio? In our example, it says that the 6 vanadium 2 plus reacts with 1 of the dichromate. 1 of the dichromate. So I cannot say C1V1 is equal to C2V2. I cannot say that the C of the vanadium 2 plus equal to the C2V2 for the dichromate, because the ratio is not 1 to 1. Then what to do? What would be the numbers here? Instead of 1 to 1, I will write, well, very easy, just make write everyone the number of moles of vanadium 2 plus divided by 6. And the number of moles of dichromate, that's 1 mole here, so divided by 5. So C of vanadium multiplied by volume of vanadium equal to divided by 6, equal to 6 of this one. So 6, 8.7 concentration multiplied by volume of Cr2 or 7. C1V1, I will make it in color so it is easy for you to understand. This is C, this is the C, and this is volume, and this is the volume. If you set up the equation, it can be very easy. It means the concentration of the vanadium is equal to 0.200 and its volume is equal to 25 milliliters. I don't need to change it because the other one is milliliter. Concentration of dichromate is 0.100. Its volume is the one that I need to find out. Divide both of them by 0.100, so the volume of dichromate directly equal to 0.20 multiplied by 25 divided by 0.100. Do this in the calculator. So I will say that 0.20 multiplied by 25 and divide this by 0.20 multiplied by 25. What is the 6? Where is the 6? Did we forget the 6? We want to set up for 6 and then we forgot it. Forgot it as 6 here. Here is a 6 here. So that's 0.100. So this 0.20 multiplied by 25 and then divided by 0.600 is equal to 8.23 milliliters difference. So again, if I want to make it easier for you, the root here, this is the direct method. So this is the direct method. Just write the n is equal to the n and divide everyone by its coefficient. So this is divided by 6 and this one divided by 1. Then you can just change the number of units into CB and so on.